Hello, welcome to CSC7132, Operating Systems and Networking. This is Brady Chen. Now, in section 9.3, we're going to talk about the disk scheduling. Okay, the most common mass storage devices are the magnetic disks. Okay, so a disk stores information on one or more rotating magnetic surfaces. So if you open a hard disk, you'll probably see a disk, or maybe there are two disks, or maybe three. They're going to rotate at the same time. Okay. So then we're going to see an arm, which is actually it's a what is called a movable arm. So if you have two or three disks, you're probably going to see two or three arms. Okay. Now here at the very top, that's called the read and the write header. So if you have three arms, then you're probably going to see three read and write header. So they can read the data simultaneously. Okay. Now, a track is used, So a track is one of the many concentric rings on the magnetic disk surface. So for example, you have a track here. You may have another track. So the data are going to be stored along the track. So in the meantime, you have also the track in the second disk and the track on the third disk. Okay. So you may actually have a track 0, which is inside 1, 2, 3. Maybe that's I call I, track I, and then there's track K. So so same thing with the second disk and the third disk. So if the arm, so you can move the arm, because the arm is actually, you can rotate the arm, left or right. So when you move left, it would actually move towards the edge of the disk, or move to the right, it will move to the center of the disk. So in order to access a particular data in the track, for example, track I, so you can move the actual arm, and point the read and write header to the track I. Okay, so the information is written onto or read from the track as the disk rotates under the read and write header. So for example, if you want to access the data on this side of the track, okay, so in that case, no matter how you're going to move the arm, you cannot reach this side, right? So in that case, you're going to rotate the disk. All these disks are going to rotate simultaneously. You're going to rotate the disk to the other side, so the arm can reach the track, so the read and write head can actually access the data. Okay, so now also a sector is used. Sector is a portion of a track and is the smallest unit of data that can be read and written with a single read and write operation. Okay, so the sector gonna look like this. Start from the center, going out. Now this is one sector. Now this is another sector, 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 sector. Okay. Now a sector has a number, so this is probably going to be sector 0, sector 1, sector 2, sector 3, and then you have a track 0, track 1, track 2, and the track I, and all the way to track K. So you're going to have a track, from the inside towards the outside, and you also have the sector. Now, so that means if you want to store the data, then the data going to be stored in one part of the track. So you can actually use the address. For example, if I store the data over here, for example, say I'm going to store the data on this portion of the track. So then you can check the track number, which is K, right? And you also check the sector number, which is 3. So this particular portion is on track K and the sector 3. Okay. Now, if you have 3 disks, then basically you can actually simultaneously. So if you want to actually read the data from these portion, then you're going to rotate the disk. So move the sector 3 to the other side. Okay. So then the read and the write header can reach that particular actually portion. Okay. So you need to rotate it, and then you need to actually rotate the disk and also, move the arm to the left or the right. So you can actually exactly move this particular, header to this portion of the track. Okay. So as was discussed in the previous slide, a disk surface consists of a large number of concentric tracks. Okay. So let's say here's a magnetic disk. Here is the center. Okay. So then the disk surface consists of a large number of concentric tracks. So let's say I have a track here. This is one track. And there's another track. Okay, so I call this, let's say, track J. Okay, now this is track K. Okay, now each track is divided into sectors. Let's say there are T sectors. T could be 1000 or 500. So T, let's say there are T sectors. So it could be from sector 0, 1, 2, all the way to T minus 1. So let's say here's the sector 0. This is another sector 1, sector 2, sector 3, and then we can continue and here's the last sector T minus 1. So now we can actually divide each track into sectors. Here's a sector 0, 1, 2, 3, and all the way to T minus 1. And here's a T minus 1, but that's the track number J, right? That's 0, 1, 2, 3. Okay, so a movable arms carries a read and write header. So let's say I have a movable arm. So let's say the carries a read and write header, which is always positioned over one of the track. Let's say the movable arm currently positioned over the track number K. Okay, here. So that's a read and a write header. So you can move this header here or here, two directions, right? So you can always move the header to one of the tracks. So currently it's over the track number K. Okay. Now, as the disk rotates, the read and write header is able to sequentially read all sectors of the current track. So, for example, here's which is particular sector. This is on track K, but it's on particular track. But if you rotate the disk, so you can actually read each portion of the track one after another, right? Okay, you can basically complete the reading of the data on the track. Okay, so basically, the speed of the disk accesses depend on a couple of actually things. One is called seek time. Now the seek time is the time to move the read and write header from the current position to the track containing the desired data. Okay, so now current position is here. Okay, so then if you want to read the data, for example, in track J, let's say you want to read the data over here in sector 2, track J, right? That's track J. So then you need to move the track, move the arm to track J, right? Move the arm to track J. Let's say you're going to move the arm to track J. Okay, so now this is gone. Okay. Now, but that's not enough because it's just to move the arm to the track J, but the data you want to read is on sector 2, but the sector 2 is not on this side. So you have to rotate. You have to rotate the disk as well. So you can rotate the sector 2, to the position. So then the read and write header can read the data in track J sector 2. Okay. So the access time depends on seek time and also the rotational delay. Okay, it's also called the rotational latency. The rotational delay is the time to wait for the designed data item to pass under the read and write header. Okay, so on average, the rotational delay is 1/2 of the time of one disk revolution. Okay, so the rotational delay is also dependent on how fast the disk is gonna rotate. Okay, a typical actual hard disk can rotate at the speed of 7,200 RPM. It's a revolution per minute. Okay, or a slower hard disk can rotate at 5,400 RPM. Okay. So, and then the third actually component is the data transfer time. So first the seek time. So you need to move the arm to the right track. And second, the rotational delay. So because you're going to rotate the disk to move the right sector, so the read and the write header can access them. And then the data transfer time is the time to transfer the desired number of bits to or from the disk. and it is directly proportional to the disk rotational speed. Okay, so the data transfer time is depend on a couple of facts. How fast the arm gonna move, and how fast the disk gonna rotate. So the most important characteristics of a disk are the disk size in bytes and the data transfer rate. Okay, you typically measure two transfer rate. One is peak transfer rate. Now, peak transfer rate is the rate at which the data is streamed to or from the disk once the read and write header is at the beginning of the sector to be transferred. Okay, so basically the peak transfer rate depends directly on the rotational speed. Okay, rotational speed. Okay, and also the number of sectors per track. Number of sectors per track. Okay, because you first, the read and write header is actually at the top of the arm, so you can actually, the rotation of speed is important, and also the number of sectors is also important. Okay, if you have more sectors, so that means the density of the magnetic disk is high. Okay. Now the other data rate is sustained data rate. Sustained data rate is the rate at which the disk can transfer data continuously. Okay. The sustained data rate includes the seek times over the multiple tracks and the other overhead in accessing the data over times. So these are two measurements. One is the peak time. Okay, the other one is sustained data rate. So the seek time and the rotational delay involves the mechanical motion of the read and write header and the physical disk rotation. So both times are in the millisecond range, and thus constitute most of the access time to the disk blocks, because that's the mechanical movement. No matter how fast it's going to be, it's a mechanical movement. It's relatively slow. Okay. Now rotational delay is easy to optimize. Okay. So given the sequence of the requests for multiple blocks on the track, so the requests are sorted in ascending order. Consequently, all blocks on the same track can be accessed within a single rotation of the disk. Okay, so you can actually rotate just doing one rotation, you can access all the blocks on this track. Okay, now optimizing the seek time is a more difficult problem because the read and write header sweeps back and forth across the different tracks. Okay, so now in this case, so you're talking about the arm here and read and write header. You can move back and forth, So that's any point in time, the algorithm must decide in which direction the read and the write header should move next. Okay, so if you have a data over on the outskirt or the data inside the disk, so you have to move towards the out or move towards the inside. So you have to move back and forth. So it's not like a rotation. It's always, the rotational delay is always because the disk always rotates at the same direction, but the arm gonna move back and forth. Okay, so it's a little bit more complicated to optimize the seek time than the rotational delay. Okay, so let's first talk about the rotational delay and discuss how to optimize the rotational delay. Now, suppose we have a disk. Okay, and then we have a track. Okay, so the read and the write header is at the sector 0 of this track. Let's talk about a track. Let's say it's a track K. Okay, so now here's the sector 0. And the read and the write header is currently at the sector 0. Now, when requests to access sectors 5, 10, and 3 on track K arrives, okay, so that means three sectors will be involved: sector 5, sector 10, and sector 3. Let's say we have sector 3 and 5 and also sector 10. Okay. Now, if these sectors are serviced in the order of arrivals, so what's the order of arrivals? So sector 5 arrives first, and then request for accessing the sector 10, and then sector 3. So that means, because currently the read and write header is at sector 0, so in order to serve sector 5, you need to rotate the disk, clockwise, right? So so then until 5 is, so the read and write is at sector 5, and then you can continue to rotate. So then until the read and write header is at sector 10. So now we serve the sector 5 and the sector 10. Okay. Now after the sector 10 is accessed, then you need to access sector 3. So then you need to actually rotate the disk counterclockwise, right? So you have to do this, So basically there are 2 disk revolutions are necessary. So first going this way and then going backward. Okay, so now if you actually track these the rotational delay, then you can check that let's say, so here's a track K. Okay, so then we have track 0, 3, 5, and a 10, right? Okay, so what we're going to do is, because the order of arrivals is 5, 10, and a 3, so that means we need to do this. So we first need to arrive 10 first. Okay, no, arrive 5 first, and then 10. Okay, and then we're going to move back to 3, right? So that means you need to rotate to this direction and then rotate back. Okay, so that's the rotational delay. To optimize this, okay, so then when the requests are reordered, okay, and serviced in ascending order, so that means it doesn't matter which one arrives first, but when I actually serve these sectors, I'm going to serve in the serve these sectors in ascending order. So that means what I'm going to do is, okay, so I'm going to actually, currently it's a sector 0, right? So the read and write header is at the sector 0. So I'm going to go into sector 3 and serve over there, and then going this way, serve sector 5 and serve sector 10. So in this case, there's only one revolution. So you're gonna run just rotate it in one direction. You don't need to go actually, the clockwise and then counterclockwise. So now, so this way you can basically optimize the rotational delay. Okay. Okay, so let's talk about the seek time optimization. Now again, we're going to use an example. Okay, now suppose we have a disk. So in order to actually illustrate this, we are not going to draw the whole disk. We only draw half of the disk. Okay, so here's the disk. That's the curve. So disk is bigger one, and that's the center of the disk. Okay, so disk is going to be like this, right? I only draw actually part of the whole disk. Okay, and then now the seek time optimization determines the order in which tracks are visited. Okay, now assume that the read and write header is at the track 0. Now let's see, where's track 0? Track 0 is the outmost track in the disk. So it's over here. So that's track 0. Okay. Okay, so now the header, the read and write header, is currently at the track 0. Okay, so that's a read and header at the track 0. Okay, so now request for track 50 and track 10 arrive. Okay, so track 50 and 10 arrives. So let's say arriving request. That's 50 and a 10. So where's 50? 50 should be far away from track 0. 10 is closer. So let's say 10 is over here. Okay, so that's track 10. Now, let's say here's 50. Okay. So now, if we want to serve the track 50 and then 10, so we actually need to move the read and the write header. We're going to rotate the arm. Here's the arm. So we're going to rotate the arm, right, to position here. Okay. Okay. So that's 50, right? Track 50. And then, serve the track 50. And then after it's done, then we need to actually rotate it back. To track 10, right? To do this. So in this case, the read and write header going to travel going this way and going back. Okay. Now, to minimize the read and write header travel distance, so the request can be reordered and served in ascending order. Let's say, okay, so we reorder it and serve in ascending order. Let's first actually serve the track 10 first, and then 50. So now in this case, so the thing's going to be quite different now. Okay, so let's see. So then you're going to travel the read and write header going to travel to here, and so let's see. okay, travel to here and serve the track 10 first. And once it's done, you're going to continue to travel to 50. Okay. And serve the track 50. So this way, the travel distance is just from here to here. Okay. You don't have to go all the way and back. You don't have to do this. So you're going to reduce the travel distance. Now, if a complication arises when you request for track 200, okay, and 40 arrives, okay, when the request, so what happens, if the request for, track 240 arrives? So where's the read and write header now? The read and write header is over here, right? It's at the track 50. So now where is track 200? Okay, so let's say track 200 is going to be over here. It's very close to the center. Okay, so that's the track 200. Now where's track 40? 40 is actually close to 50, right? Now that's 40. Now here we have a kind of tough situation. The algorithm must decide whether to continue, so whether you're going to continue, to travel all the way to track 200 and serve the track 200 and then travel back to track 40, right? Or we're going to go the other way. We first actually visit track 40 and then, so we first move back, serve track 40 and then move forward to 200. Now, which way is better? Certainly the second approach is much better, right? So if we draw this diagram here, let's see. So let's see, here's the, so now the arriving request is going to be, okay, 10, and then we have a 200 and a 40, right? So let's see, here's the track. Okay, so here's track 0, 10, and 50, or 40, 50, and then 200. So remember that initially we actually, travel from track 0 to 10, and then travel to 50, right? And then now 240 arrives. So using the first approach, because 200 arrives before 40, the track 200 arrives before 40, right? So we're going to service the track 200. We're going to travel all the way to here. And then travel back to 40. Okay. Or, so the alternative way is, if we try to minimize the travel distance, so right now we are at the 50, right? So then we're going to travel to 40 first. Okay. And then after you complete the track 40 and travel all the way to 200. Now it's clear that to service track 200 before 40 requires travel of, let's see, what's the travel distance? So let's see, you're going to travel from 50 to 200, so that's 150, right? And then you're going to travel all the way from 200 back to 40, That's another, let's see, 160, right? So the total travel time gonna be 150 plus 160 travel distance. I'm sorry. Now, what's the other approach? So from 50 to 40, you're gonna travel distance of 10, and then from 40 to 200, you're gonna travel 160. Okay, so the total travel distance is gonna be 10 plus 160. Now that's 170. Now the other one is 310. Certainly, this is much better. This is optimized. Okay. So this way, so if you actually, travel in ascending order, then the seek time will be optimized. So the simplest approach to disk scheduling is to service all requests in FIFO order. So FIFO is always the simplest approach. Now, which is the order of arrivals? For each request to access a sector on track T, the read and write head moves to the track T. Now, the number of tracks traversed by the read and write header using FIFO scheduling can significantly be reduced when requests are reordered prior to moving the read and write header. So if we don't actually follow these FIFO and then we reorder the requests, it may actually reduce the the travel distance for the read and write header. Now this actually leads us to the shortest seek time first. Okay, so now the shortest seek time first scheduling algorithm, or sometimes called SSTF scheduling algorithm, considers the list of all pending requests. So now, if the read and write header is at the current position, and then for all the pending requests, okay, so now it considers the list of all pending requests and always selects the request that requires the shortest travel distance from the current position. So whatever the position it is for the read and write header, and then it always travel to the request that requires the shortest travel distance. That's the SSTF. Now let's take a look at the example. Okay, so let's take a look at the example of FIFO scheduling algorithm. Let's assume the arriving requests are track 5, 12, 3, 7, and 4. Okay, so let's take a look at the FIFO. Okay, scheduling. So let's say this is actually the track 0. So initially the read and write header is at the track 0, and then we have track 3, 4, and the 5, right? And then we have 7 and 12. So now, initially the read and write header is at track 0. So when 5 arrives, the read and the write header travel to track 5, right? And then what's next? And track to 12. And then next one's 3, so we have to actually travel back to 3. And then from 3 to 7. And then from 7 to 4. Okay. So now what's the distance just traveled? Okay. So first let's see. So we traveled like from 0 to 5, we traveled 5. And then from 5 to 12, it traveled 7, right? And then from 12 all the way back to 5 to 3. So that's basically, that's a number. And we traveled to 9. And then from 3 to 7, traveled 4. This traveled 4 tracks. And then from 7 back to 4, you travel 3 tracks. So the total, this, travel distance of the read and write arm is 5 plus 7 plus 9 plus 4 plus 3. So that's total of 28 tracks. Okay. That's for the FIFO. So we have to exactly follow the order of arrivals. Okay. So now let's take a look at the example of SSTF scheduling algorithm. Now assume the arrival requests are still 5, 12, 3, 7, and 4. Okay. So then we have still have the track 0, and then we have a track 3, 4, 5, 7, and 12. Okay. So now with SSTF, the read and write header moves from the current track 5. Okay. So first, okay, so you're gonna travel from 0 to 5. That's the first one. Okay. Now during this time, now the next track, requests just arrived at 12, 3, 7, 4. They all arrived. Okay. So in that case, so then the read and write header moves from the current position 5 to the nearest request track, which is track 4, even though track 4 arrives the last one, but these are all the pending tracks. So instead of actually moving to 12, which is the next one arrives, but you're going to move back to 4. And now what's the next one? You're going to move back to 3. Okay, so now we actually, service the track 5, 4, 3, and then what's the next nearest one? The next nearest one, you have actually track 12 and 7. So the nearest track is 7, right? And then 12. Okay. Now we can see that it's definitely the travel distance is optimized, right? So let's check. So first you travel 5, and then from here 5 to 4 you travel 1 track, and then you travel from 3 to 7 you travel 4 tracks, and then from 7 to 12 you travel 5 tracks. So the total distance traveled is 5 plus 1 plus 1 plus 4 plus 5. So that's 16 tracks. Okay. Certainly, it's much better than the FIFO, right? Now, what's the drawback? So the downside is that a string of new requests for trucks in the current vicinity of the read and write header would postpone the servicing of the more remote trucks 7 and 12 indefinitely. Now, what about, when you complete, for example, when you complete the servicing, the truck 4 and then servicing the truck 3, and a new request arrives, which is actually in, for example, truck 2 and then truck 6. So now the truck 7 and the 12, particularly 12, were never going to be able to get serviced. So that's the problem with the with this seek time optimization with the SSTF scheduling algorithm. So the next scheduling algorithm we're going to discuss is the scan scheduling algorithm. Okay, now the scan scheduling algorithm mimics the behavior of an elevator in the building. Okay, let's see. Suppose if everyone used the elevator, you probably still remember that if we have a couple of floors. Okay, so now there are different peoples, at the different floors, they are requesting for services, right? Okay, so if the current elevator location is here, and it's moving up, so then the elevator is going to keep the current direction. It doesn't matter whether the guys, let's say that's floor 2, that's floor 3, 4, 5, 6, 7, right? So it doesn't matter whether the person in floor 2 actually pressed the button, but the elevator is still going to go up, okay? Because there are people, at the floor 6 and 7. So you're going to serve the person in floor 4, and then continue to move up to floor 6, and then move up to floor 7, and there's no more actually people above floor 7. So then you're going to start to travel down, and then start to serve the 2. But if during which time, if people, there are people at the floor 5, press the button, it will stop at 5, and then continue to travel down and stop at 2. Okay, so that's basically how elevator works. Now, scan scheduling algorithm basically mimics the behavior of an elevator. Okay, now, so using scan scheduling algorithm, the read and write header maintains the current direction of travel, and the services all request sequentially in the current direction. When the outermost request is reached, okay, then the direction is reversed, and the algorithm services all requests in the opposite direction. So now let's take a look at the same example we just discussed. Okay, so let's suppose that the arriving requests are truck 5, 12, 3, 7, and 4. Okay, so now let's say this is truck 0, 3, 4, 5, 7, and 12. So the read and the write header is initially at the truck 0. So when 5 is request first, so you're going to travel all the way to truck 5, and so then 12 actually arrives. So then it doesn't matter. It continues to travel, okay, in this direction, because there are more trucks ahead. So the next one going to be 7, and then the next one going to be 12. So 12 is the outmost request, right? There's no more request after 12. So then the read and head actually start to change the direction. It just moved back. So the next one is request 4. So it travels actually like from 5, 7, 12, and then 4, and then continue to travel to 3. That's the end. Okay, so now let's see what's the travel distances. Now from 0 to 5, that's 5 tracks. And then from 5 to 7, that's 2 tracks. And from 7 to 12, that's 5 tracks. Okay, and then from 12 all the way back to 4, that's 8 tracks. And then that's 1 tracks. So the total distance traveled is 5 plus 2 plus 5 plus 8 plus 1. So that's total of 21 tracks. Okay. So the now what's the performance? Remember the FIFO, I believe it took like 28 tracks. The SSTF is shorter, right? So the scan scheduling algorithms, basically the performance of a scan scheduling algorithm lies between the performance of a FIFO and the SST algorithm. Okay, but the starvation is eliminated. Okay, so now since each request is guaranteed to be served within one sweep of the R and W header, however, the access time to different tracks is not uniform. Since the R and the W head sweeps back and forth, tracks closer to the middle range have a great chance to be served quickly, and then tracks at either extreme of the disk, either on the close to 0, track 0, or close to the maximal track numbers. Okay. Okay, so let's take a look at a variant of the scan algorithm. That's called a C-scan scheduling algorithm. Okay, so the C-scan scheduling algorithm services requests in only one direction. So when the outmost request is reached, the read and write header sweeps back to the opposite end of the disk. Sweep back to the opposite end of the disk and starts servicing the request again in the same direction. Okay, now let's take a look at this. So here we're talking about a C-scan scheduling. Okay, so here's the track 0, track 3, 4, and 5, and 7, and 12. Okay, again, so when the read and write header travels all the way to track 5, and the service is track 5, right? And then, so 5 is services. And then the next one going to be 7. And 12. So now, so there's no more actually tracks after 12. So that's the, outermost request, the track. Okay. So then the read and write header sweeps back. Okay. Sweeps back. It will sweep us back all the way to the opposite end. So it's never going to stop at the 4 because there are still actually some track before 4, right? Which is track 3. So you're going to swipe all the way, past 4 and to 3 because 3 is the opposite end. That's the 1. So you can travel from here and then start to service 3 and then service 4. Okay, so in this case, it's only actually travel from 12 all the way back to 3. It's never going to service any track. And then once it reaches the opposite end over here, and it start to services again, the track 3 and 4. So let's see, what's the travel distances? So from 0 to 5, it's 5. Okay, 5 tracks. From 5 to 7, that's 2. And from 7 to 2, that's 5 again. Now this, you're going to travel all the way from 12 to 3, that's 9, right? And now start from 3. You're going to service track 3, and then service track 4, that's travel 1. So the total travel distance is 5 plus 2 plus 5 plus 9 and plus 1. So that's 22 tracks. Okay. So that's the C-scan scheduling algorithm. It's pretty much the same as scan, but instead of actually servicing the tracks in the opposite direction, it does not. It just travel all the way to the end, opposite end, and it start to, always actually, follow the one direction to services the tracks. Okay. Okay. So in this last slide, we're going to talk about the performance of the scan algorithms and the C-scan algorithms. So the performance of the scan algorithm lies between the performance of the FIFO and the SSTF, right? But the starvation is eliminated. So that's a good thing. Okay. Now, again, as we mentioned, the access time to different tracks is not uniform. Since the read and write header sweeps back and forth, tracks closer to the middle range have the greater chance to be serviced quickly than tracks at the either extreme of the disk. Now, unlike scan, C-scan guarantees a uniform access time to all tracks, because the read and write header services all request in only one ascending order. Okay, so that's the position in the middle range of the disk conveys no advantage over any other positions. So it just guarantees the uniform access. Okay. Thank you.